The normal distribution. So here we're looking at a continuous random variable which can take any one of infinitely many values. And the probability that a continuous random variable takes any one specific value is 0. But we can write the probability that it takes values within a given range. So the normal distribution is a continuous random variable. Other key features that we need to understand here is that a continuous random variable has a continuous probability distribution, which can be shown as a curve on a graph. And the area under a continuous probability distribution is equal to 1. And such a continuous normal distribution can be shown here through this curve, and the area underneath this curve is 1. The continuous variable generally encountered in real life are more likely to take values grouped around the central value than to take the extreme values. And that's usually what happens in reality, most of the distributions that we come across. So the normal distribution is such a distribution where we have a continuous probability distribution that can be used to model many naturally occurring characteristics. A majority of the things or majority of the heights of people within a given population will lie in the central mean location. Weights of tigers in a jungle, they will tend to lie, the majority of them, or the mean or the mode tends to lie near a middle value, and the weights, higher weights and lower weights tend to tail off. There'll be fewer of those happening. Okay. And also other examples of continuous variables that can be modeled using the normal distributions are errors in scientific measurements and size variations in manufactured objects. Majority of them will be within the actual size that we want, but there'll be one or two in either extremities, higher or lower end, which will not be to the size that we wanted. So such a distribution becomes a bell shape, as we have here. This is a bell shape. A bell-shaped curve is the curve for a normal distribution and is symmetrical about the mean. The mean value is right at the center here. So here the mean is 175 in this particular example for height. And we can model the heights of adult males in a city, for instance, using a normal distribution. So the mean height of adult males would be 175 centimeters, and the standard deviation is 12 centimeters. So then we would write it down as x, which is the height of adult males, can be approximated by a normal distribution with a mean of 175 and a standard deviation of 12, or 12 squared being the variance here. So the normal distribution has the following parameters. It has mu, which is the mean, the population mean, and sigma squared, which is the population variance. It is symmetrical, i.e. the mean, the median, and the mode are equal to each other. It has a bell-shaped curve with asymptotes at each end, and it has a total area under the curve which is equal to 1, which represents all the different outcomes, i.e. the probability of all the outcomes add up to 1. And it has points of inflection at mean plus sigma, mu plus sigma, and at mu minus sigma. Other key features that we need to understand about the normal distribution is that approximately 68% of the data will lie within one standard deviation of the mean. Okay, so what that means is mu plus or minus one standard deviation, all our data, 68% of the data will lie. And then we have 95% of the data which will lie within 2 standard deviation. So that's mu plus or minus 2 standard deviations. And then 99.7%, which is almost all of the data, will be within 3 standard deviations of the mean. So mu plus or minus 3 standard deviations.